All right, so welcome back. So in this brief last part of Lecture 5, Part D, we are going to extend, and again, without going into much detail, the results that we've gone through for continuous time to discrete time. If you're interested in discrete time systems, this is the equivalent. Now, discrete time systems are, don't want to say they're more complex than continuous time system, but they don't have quite all the nice properties that continuous time systems have. Well, remember, for example, for discrete time systems, there's no obvious metrics for settling time and percent overshoot and all that kind of stuff. In terms of eigenvalues, and so we don't go over destabilization for discrete time systems. Moreover, the very nice, very elegant results we have for continuous time systems on the equivalence between controllability and reachability we had for continuous time systems just don't hold, because discrete time systems have sort of pathological cases. Now remember, controllability was the ability to find an input, a continuous input, which would, for any initial state, allow you to force your system to zero in finite time, right? So it was like, say, we could get here from here in finite time. Whereas reachability was our ability to get from zero to any other state in finite time. Right. That's reachability, and that's controllability. Okay. Now, obviously, they're not equivalent for discrete time systems, because we consider this, we can just look at this pathological case here, where the dynamics are zero, right? So no matter what your previous state was, you just set the next state to zero, right? So obviously, this is controllable because every initial condition goes to zero in time 1. But obviously not reachable, because there's nothing we can do to drive this system to anything but 1. So it's definitely controllable and definitely not reachable. So obviously these problems are not going to be equivalent. That said, we can, if we sort of gloss over these pathological cases, we can sort of extend some of the results that we had for continuous time systems to discrete time systems. So, for example, we have a discrete time controllability Gramian, which is the obvious logical equivalent of the continuous time one, where we've just replaced the integral with a summation, and we've replaced e to the at with a to the k, right? So remember, that was sort of the solution x of t equals e to the at x naught versus xk equals a to the k x naught, right, for discrete time. So we just replace that exponential with a to the k, and we replace the integral with a summation, right? So it's the obvious natural equivalent. And then again, we have infinite time horizon here because, right, finite time horizons don't work as well in discrete time, right? Because in continuous time, there's an infinite number of updates for any finite time interval, whereas on any finite time interval for discrete time systems, there's only a finite number of updates. So that finite time controllability Gramian doesn't work as well for discrete time systems. So we'll limit ourselves to infinite time. Right. So that said, right, it's relatively easy just to plug this sucker in to this LMI and show that the system is controllable. If the system is controllable, then this Gramian is the unique solution to this Lyapunov equation here, which we'll call an LMI just for the sake of calling things LMIs, but there's no inequality here. Right. So if you can find such a W, right, that satisfies this exactly, then that is the controllability gramming in discrete time. Now, we won't make sort of the finite time equivalent, and we won't relax this inequality as we did for continuous time, but if we do solve it exactly, that gives us the Gramian. And we can also construct controllability ellipsoids, but again, the interpretation is more dubious in the discrete time case. So, you know, that was like, well, a lot of lecture slides we just covered in the continuous time and one for the discrete time. And so now we skip to part C, or the equivalent of part C for discrete time, which is the controller synthesis problem. And again, the feedback controller in the discrete time case looks like this, right? Where we have measurements of, from sensors, of the state, that's the full state feedback, static full state feedback. There's a typo here, by the way, that should be K. So static full state feedback controller that we're looking for in this case. So formulating this is an optimization problem, right? Here's our variable K. I'll switch to the smaller pen here. And we want to, of course, close the loop, right? We plug in this equation here into UK, right? It becomes, right, KXK. And then once we close the loop, it becomes sort of an autonomous system with no input, because we've applying the input, but we can analyze it autonomously. Now, you know, in discrete time, there's always sort of like, there's this issue with K versus K plus 1. It's such a hassle. So technically, I mean, you could have, a more realistic implementation, right? Because you have this measurement time, Kx minus 1, but we're not gonna go there, right? So we'll just assume we're closing the loop in real time. We can simultaneously measure and update the input. Yeah. Right. So our goal then, right, is to find our K such that A plus BK, that autonomous closed loop system, has desired properties, and in particular the desired property, really the only one we have to work with in this is stability. So specifically, we want this closed loop system to be Schur. That is, to have eigenvalues of less than 1. Right. So again, obviously, we could solve the problem of eigenvalue assignment for continuous time. I mean, the problem, the optimization formulation is no different, right? Eigenvalue assignment is okay. Right? Just solve it exactly the same way we did previously. Right? You just plug A plus BK into Acker or place, and you're done. Of course, we're interested in solving optimization problems, however, because we'd like to sort of stack these constraints on top of each other. So we'll think about it from an optimization standpoint. And so in this case, if we just apply the Lyapunov inequality, right? Here's the Lyapunov inequality. Right? Then we get an optimization problem. Sure, here we have two variables. But the problem is even worse than a BMI, which we had in the previous slides. Occasionally you can solve BMIs, right? There are tools which they're BMI solvers. They don't work very well. They're all sorts of like local minimum, but they're BMI solvers. There are no tri-MI solvers, right? This is a TMI. Too much information. Too many variables earlier. Too many multiplications or something like that. Anyway, so you see there's a k here which multiplies by a p which multiplies another k, right? So this is really quite intractable. So if we pose a stabilization problem as an optimization problem, the natural formulation is this one, which is, of course, intractable. Hopefully, though, we'll be able to reformulate it in terms of an optimization problem, which is tractable. And we have a couple clues that we're going to be able to do this. This sort of framework we see here is actually a pretty good indication that we can solve this. And in this case, the tool that we're going to be able to solve it, we really go through all of our tools in this in our toolbox in this lecture. Before we had the duality tool, we had the variable substitution tool, and in this case, we're going to add in the Schur complement tool. Right, so if you just parse this like intuitively and get some intuition into how these things work, this is sort of a pseudo-quadratic in one variable with the p appearing linearly otherwise. Right, so you should be on the lookout for optimization problems that look like that because they're naturally well suited to the Schur complement trick. Schur complement's not a trick, but well, I don't know, maybe it is. So in particular, here's our Lyapunov inequality, and we'll apply the Schur complement to it. The way I do it in this particular lecture, I honestly, if I were you, I would like apply the Schur complement directly to this. The way I do it in this lecture, however, is I dualize it first, and then apply the Schur complement, which no, it's not probably the most straightforward way of doing it, but hey, that's what I've done. So basically, I dualize this. I apply a duality trick here. By multiplying by p inverse on both sides, right? That doesn't change the inequality because p being strictly positive, right, is full rank, and so also symmetric, so we don't have the transpose issue showing up. So I multiply p inverse on both sides. Well, obviously, you multiply p by p inverse twice, and it becomes p inverse, right? And then the other p inverses nothing happens to them. They just show up there and there, right? So that's the only thing that's going on here, is that this is p inverse, p inverse, right? And that goes to p inverse. So now, as our second step, I guess, we apply the Schur complement formula. Right, so this is Schur complement says that this goes to there. Right, this is a standard Schur complement. Right, we've got something here, in the inverse of something here, so that term goes down there, and then we got these two things multiplying on the left and the right. It's the same thing. And so this one goes over here, this one goes over there, and so we get this this formulation of the problem via the Schur complement, just apply Schur complement, which is equivalent to the original problem, but has the advantage now that it's bilinear, BMI. Which is better than a trilinear. So actually, it wasn't even trilinear matrix inequality because it was quadratic made by, anyway. So it's something in a slightly better form. And moreover, we can see that our variable substitution trick is going to work here. So we're going to make that z. And then we're going to swap out our variables p inverse with x. X is p inverse. So we showed on the previous slide that this was representable as P inverse A plus B K transpose A plus B K P inverse. Right? So that's equivalent to that, right? And so we're just going to do show that problem 1 is equivalent to problem 2 in the same way we had. Well, actually, we just did that. But problem 3 here, down here, I suppose, is equivalent to the original stabilization problem. And we can see that, right, because here's our LMI, right? We're going to propose if X solves this, then X equals P inverse, and Z equals KX, which is P inverse, solves this problem as well. So we can just look at this, right? And this is KX. Well, that's going to be Z, and so that term down there just falls down there. And there's really nothing else we need to do. The logic is identical to the controller synthesis problem we had before. So we have an LMI now, right, where we've applied a combination of duality, a Schur complement, and a variable substitution trick, which allows us to solve the controller synthesis problem for discrete time systems. Right? And if we solve this LMI, we can then afterwards construct the controller using the solution to that LMI. Z is not the controller, it's the control variable, by inverting X here. Right? And X is, of course, invertible because it's positive definite. Right? And so if this is feasible, and we use this feedback controller, then the closed loop system is stable. It's Schur, or Schur it's stable. So again, a relatively straightforward extension. Finally, just to wrap up the lecture, we have also a stabilizability criterion. This is where the system is not controllable, so it's a little bit weaker. Again, it's that equivalent. Where, remember, in continuous time, this was A transpose P plus PA, I think it was. And go double check that. AP, actually, it's in the dual formulation. So we have AP plus AP transpose less than actually it was positive, gamma B transpose. That's what we had in continuous time. And there's a discrete time equivalent, right, where we're just taking this dual version of the Lyapunov inequality, and I guess we could put a gamma here as well, by the way, if we wanted to. And so this weakens the condition that the system be Schur, right? It only has to be Schur. The eigenvalues only have to be negative for states which are not directly affected by our inputs, right? So this is not less than or equal to 0, right? And so that means that there's a control input which will drive the states which don't naturally go to 0 to 0, right? And the solution is presumably a reverse time version of the discrete time controllability Gramian, but again, I don't give the solution here just because the focus here is not on discrete time, but for those of you bold enough, maybe you want to put together a wiki page for the course wiki. You can find the solution to this inequality. All right, so that wraps up our sort of classical notions of reachability, controllability, stabilizability, and all the rest. The equivalences hold very strongly in continuous time, slightly weaker in discrete time. In the next lecture, we'll go briefly over the problem of observability and show that many of these things hold directly just from the mathematical machinery we created in this lecture using a duality argument. But I will leave that exposition for another time, and wish you well.